Right. Yes. Yeah. Good afternoon, everyone. This morning you probably learned a lot about the recipe of training large multimodal model, including data, model design, and the fine-grained vision capability. I hope you enjoyed a lot. So in this talk, I'm going to walk you through the important role of vision in large multimodal models. I believe you should be interested, considering this is CVPR, and also I'm sure most of you are probably work on vision. Yeah, so in this figure, actually, this is a typical model architecture for large multimodal model. It usually consists of a vision encoder and a large language model, right? And taking the image as input and also a text prompt. And for example, the text prompt is where is the tall building in the image, then the answer could be, okay, the tall in the image is a Space Needle. Actually, it's a very recognizable kind of landmark in Seattle. So probably you are going to plan to visit there. Yeah. So this is whole kind of typical architecture of large multimodal model. So in this talk, I will mainly focus on the vision part, as highlighted by this red box. So more concretely, actually, I will walk you through the vision encoder as a vision tokenizer for large multimodal model. And I will also hear about what's the advanced techniques for coping with these visual tokens. And finally, I will also mention about the visual prompting. So it's image, right? So we should develop some kind of visual prompting, not just only the text prompting for large multimodal model. So let's first focus on the first part. So the question is pretty simple, right? So what vision encoder is a good vision tokenizer for large multimodal model? This is a very important question and also a very kind of open question for us to ask because we really want to build a very, very capable large multimodal model. So let's first have an overview of vision encoder. So since the era of deep learning, actually we have seen a large amount of work to train the vision encoder. Starting from left to right, it can be the supervised learning trained by some kind of cross entropy loss with ImageNet dataset or some other kind of classification dataset. It can be mask modeling like MAE. It can be autoencoding like VQVE or VQGAN. It can be self-distillation, Dino V2. And the reason actually there are also some kind of multimodal vision encoder like CLIP and CCLIP and etc. So actually in the context of large multimodal model, actually we are seeing a very intuitive or counterintuitive fact. So almost all large multimodal models use multimodal lambda vision tokenizer or vision encoder, right? And a few of them use the Dino V2 for vision tokenizer to augment the original CLIP vision encoder. And some of them, even worse number of works actually use VQVE when image generation or image editing task actually is required and is needed. And of course, thus far, I did not notice anyone use, for example, ImageNet 22K trained model or MAE trained model. That's surprising, right? So based on this, actually, we studied some kind of, this kind of phenomenon behind the scene. So we have some kind of simple ablation on different vision encoders. So we started with tiny llama because it's very small. And then we follow the Llama 1.5 training recipe. And we switch the vision tokenizer or vision encoder from CLIP, CCLIP, Dino V2, and some kind of diffusion model, right? So you can see here on Citybench, which is pretty kind of wide range kind of benchmark. You can see here actually CLIP and the CCLIP actually outperform the other type of vision tokenizer like Dino or diffusion or kind of VQGAN based kind of tokenizers. So this is pretty kind of straightforward and explains why, okay, people usually using this kind of contrast learning or multimodal contrast learning vision tokenizer. And even we dig into the details. So we did some visualizations by extracting the feature from different type of vision tokenizer, including Stable Diffusion, CLIP, and CCLIP, and Dino V2, etc. And we can see that, okay, if we project the visual concept, the images from ImageNet 1K to the feature space, we can see here. So the Stable Diffusion actually totally messed up the different categories, right? So here actually different columns represent different categories. So here the CLIP and the CCLIP and actually they are slightly better than Dino V2. Actually, this kind of visualization indeed explain why actually we are seeing some kind of trend across different vision tokenizer for large multimodal models. I think this is very interesting, right? And likewise, actually, in other works, actually, recently, people also studied this kind of aspect by switching different vision tokenizers. For example, on left side, we can see the prismatic VRMs. Actually, they also tried, okay, ImageNet 1K and Clip and the C-Clip. You can see here, actually, the ImageNet 1K actually is pretty bad, right? So that's why no people use the ImageNet 1K or ImageNet 22K per channel vision encoder as a tokenizer. On the right side, actually, another work called Brave further study different type of multimodal contrast learning kind of vision tokenizers. Somehow, actually, different vision tokenizers, even, okay, they are all trained with multimodal contrast learning, actually behave slightly different across different benchmarks. So, and in this sense, actually, we can conclude that, okay, the vision tokenizer, actually, we usually, for vision tokenizer, we usually tend to use this kind of multimodal contrast trained kind of vision tokenizer for large multimodal model. But further, if we think further deeply, we look through all of the vision tokenizer, we will see, okay, all of the model were trained in an image level kind of task. So usually the image was resized to 224 or 336. Actually, this resolution is pretty low, right? So people actually have been trying to further enhance this kind of vision tokenizer, even though they are better than Dino V2, they are better than ImageNet 1K, etc. But people are still trying to further improve the performance. So the first type of enhancement is high resolution. So even though, okay, the original clip model actually only can take 222 or 336, but for example, in Lava 1.6, so the authors proposed to crop the image into multiple sub-regions, sub-images, and encode the sub-regions one by one using the fixed size vision encoder, the clip large 336. And this is one of the earlier work that trying to expand or extend the capability of the fixed size vision encoder. And later on, actually, some other work like Lava UHD and Intel LMM exposer, actually, both of them are following similar kind of strategy, cropping or dynamic cropping the image into multi-crop and encode each of the crop through the fixed size clip model. And then, okay, merge them together and feed the merge token into the large language model. So both of them actually are following the similar kind of pipeline. And later on, actually, people jump out of the box to think about, okay, what is kind of vision tokenizer we can use, which can adaptively support different type of resolutions. Actually, we have some free lunch, like ComNext. So because we already have some ComNext kind of open clip model, and in Mini Gemini and ComLlama, actually, both of them are trying to leverage this kind of high resolution supported kind of vision encoder to encode the image. And both of them actually are showing very good capability. And also, it does not require even tune the vision encoder to support different type of resolutions. So this is very kind of straightforward, right? However, even though, okay, people trying to leverage, okay, the high resolution, leverage the multi-crop strategy to enhance the vision tokenizer. So it still probably cannot understand a lot of details, for example, the depth information, the layout, and etc. Because this information actually can hardly be learned by some kind of image level contrast learning task, like clip or some other type of image level task. That's why actually people are seeking to enhance by ensembling. So there are different type of vision encoder, vision tokenizer for depth, for detection, for segmentation, for OCR, for layout, etc. And based on this, actually, one of the earlier work is called VCoder. So the authors proposed to enhance the original vision encoder by extract the depth information, extracting the mask information or segmentation information through some off-the-shelf vision encoder, and then feed all of the information together to the model. And they only tune the connector, the MLP, between the language model and the segmentation or detection network or depth estimation. So finally, it turned out that, okay, so this kind of enhancement can significantly improve the fine-grained understanding of the large multimodal model. On the left side, you will see even the original GPT-4V cannot count the number of persons in the image very precisely. But if you have more kind of information about the depth, about the segmentation mask, actually this additional information can significantly help and guide the model to answer the question concretely and precisely. And yeah, as you can see here, this is the only part. The was is tune the model. And another work is trying to enhance the original clip model with another dyno V2 in the sense that, okay, on the top left side, given the same image, the clip and the dyno V2 will project the image into different locations in the feature space, which indicated that, okay, there's some kind of complementary between the more semantic aware vision encoder clip and the more spatial or more fine-grained aware vision encoder dyno V2. Based on this intuition, they develop different type of combination, like additive mix of feature between these two type of feature, or okay, the interleave the mix of feature between these two type of feature. And it turned out that, okay, this combination, even though they finally use a similar number of vision tokens, actually it can improve the fine-grained and understandability very well, even though probably it does not necessarily improve the lava bench or the POP, but this is very kind of intuitive and reasonable, right? So later on, people are becoming more progressive and think, what if, okay, we can enhance more? So what if we can integrate more vision experts? For example, in Mossy, this work actually, they exhaustively integrate so many kind of vision tokenizers or vision encoder, like clip, like layout information, like segmentation, like many others. So they just develop a very simple kind of poly expert fusion MLP, which is literally some kind of simple neural network like MLP working former, and then they have some new strategy like multi-pass to single token projection, which is pretty straightforward and simple. And the whole model actually can significantly improve the performance across the board, especially for some kind of domain-specific task like layout understanding, like counting, like fine-grained kind of spatial reasoning, etc. So likewise, actually, there's another work called Brave. Very similar, right? So they also use a Q-former. And the reason why people use Q-former is that they really want to condense the number of tokens, because we cannot handle, okay, a very long sequence of visual tokens. So due to the limited context length in language model and what's the compute cost, right? And that's why actually people usually develop this kind of Q-former style architecture to condense different visual tokens from different kind of visual tokenizers, and finally put these kind of visual tokens into the larger model. And indeed, okay, if you look at this different type of vision tokenizer, actually each different vision tokenizer, so if you look at this table, you will see, okay, the Brave model actually can significantly outperform the previous work by integrating so many type of vision tokenizers. And this work further think about a new strategy. So one of the previous works actually heuristically stitch and combine the vision tokenizers, right? So this work proposed to adaptively or learn how to stitch the vision tokenizers. So they propose a strategy called adaptive mixture of experts. So that's why actually they propose a new training stage to train a kind of context-aware expert routing by collecting some kind of routing instruction tuning data. Of course, you will see that, okay, the model still requires some kind of, some type of instruction tuning data to teach the model how to do the merge, how to do the assembly automatically and dynamically. But this is one step forward to make this kind of assembling of vision experts more adaptive, more dynamic, and more capable probably. And again, okay, this figure actually should give you some kind of sense about different capability from different vision tokens. Even, okay, they even studied, for example, detection and some even picks to structure, this kind of layout or kind of fine-grained layout understanding. And you will see here different vision tokenizer indeed, okay, are capable or are good at different type of subtasks, right? But finally, they have some kind of adaptive fusion, and finally, they can achieve the best across the board by using the top one or two vision tokenizers for each of the individual tasks. This is very interesting, right? And another work also apply this kind of mixture of experts, but it's not a mix of vision tokenizer. It's a mix of MLP layer, mix of kind of different self-attention model in the vision encoder. This is common. So this work actually trying to integrate different type of techniques from the MOE research community, right? They propose a so-called co-upcycled MOE block that basically duplicate, right, the original MLP, the original self-attention layer to multiple, and then the lane to smartly select a subset of the experts from the pool and finally enhance the performance. So this is another type of strategy to enhance the vision token network. So to summarize, so to answer, what a vision encoder is a good vision token network for large multimodal model, at least for now, actually, we are seeing that, the multimodal pre-trained vision token network, like CLIP, C-CLIP, etc., is still the best single one, but still not sufficient. And also, multi-crop strategy can support much higher resolution, use fixed size encoder, and unfortunately, this will introduce some kind of burden or overhead to the whole kind of system, which I will talk about later. And the last point is that, the mixture of vision encoder or vision components in the vision token network actually can further enhance the performance, but still require more kind of study regarding how to adaptively, how to automatically merge or ensemble the vision token networks. Okay, so yeah, I just talked about the vision tokens, right? So we have a lot of vision tokens. So how to cope with these vision tokens for large multimodal, especially for high resolution image, especially for the multi-crop strategies. So the curse of visual tokens. So I'm sure you guys actually are thinking about this question. So how to reduce the number of visual tokens so that I can put the vision tokens into the language model, right? This is a very crucial question to ask. So people usually do think of, so we have a very kind of long sequence and how to reduce the number of tokens. Of course, this is very straightforward and solution to this problem, right? So in terms of the solution, so the early stage is to handle visual tokens like Q-former, the length, some kind of encoder-decoder architecture by using some kind of learnable query to condense the original long sequence of visual tokens into a small set of, for example, 100 or 200, etc. And also manageability to V2 also propose even simpler one. Just do some kind of concatenation for the adjacent visual token, and then do some kind of simple projection to project the high dimensional feature to the low dimensional feature and use this as vision tokens. Pretty simple and straightforward. And later on, there are some works try to further improve the performance and also do this kind of token reduction. So S2, the scaling on scales, also use a similar strategy, but the difference is that, they first crop the high resolution image into multiple crops and then encode the image. And instead of, simply, flighting the high resolution feature map, the 32 by 32, actually they first do some pooling and then do the dimensional concatenation. This will actually, you can condense the high resolution information to the 576 number of vision tokens. So this will actually, they improve the performance across different tasks, especially for the task like, the V-star, which require this kind of high resolution image understanding, even though, they have the same number of visual tokens. And another work is called the plumage. So this work actually is trying to merge the visual tokens using some strategy like clustering. So the first select the top candidate tokens and use some clustering to class the other tokens into these class centers. And finally, merge them and can calculate the new center and use these new centers, class centers as a visual tokens. So this way, actually, they can significantly reduce the number of tokens. If, as mentioned in the paper by the authors, they can even, condense the original kind of number of tokens to maybe 25 per stage, but still maintain very good performance. You can see here, this table actually demonstrates that. And recently, actually, we also have a new work called Matryoshka, multimodal models. So this work is not only about condense, it's also about adaptive. It's also about controllability. So when we borrow the idea from the Matryoshka, this is just a toy from Russia, right? So this strategy actually tells us that, we can put the tokens in a nested manner. So the first token, we can use it for the task. The first 2 token, the first 5 token, the first 100 token, the full set of tokens. We can adaptively control the model to take a various number of tokens as input to to perform different type of multimodal tasks. So we observed that, okay, so based on this kind of adaptive training stage, actually we can maintain a very kind of flattened kind of performance across different number of tokens compared with the baseline, compared with the other kind of method. And also we draw an oracle on the top left corner. You will see, okay, we are still far away from the oracle. The oracle means that, okay, if we know the task, and then if we know, okay, the minimum number of tokens which can make the task correct, then, okay, you will see there are still a huge gap, which means that there are still a lot of space for the improvement. And interestingly, actually, there are another concurrent work called Matrix query transformer. So it's pretty similar and related, I would say. And the difference is that, okay, delivers the Q-former. So Q-former originally actually is proposed to condense the number of tokens, right? But later on, actually, they proposed to not only condense, like what we did in Matrix multimodal models, not only condense, not only compress, but also control and it in an elastic manner. So they also have some kind of similar finding in the paper when the gradually reduced number of tokens fit into the language model, actually they can maintain much better kind of trend. The performance drop actually is much, much smaller, much minor compared with the baseline. And later on, actually, we further propose a new strategy. So we want to jump out of the box. So all of the perverse works, including the last few works actually I introduced. So they are trying to think of the token sequence, right? So from left to right. So high resolution and then sequence, and the low resolution is still sequence. But in this work, actually, we propose a deep stack. So we want to stack the visual tokens and reorganize them into different layers, and different layers fitting into different transformer layers. So in this way, we do not, okay, so condense the visual information very aggressively by only feed them into the input layer of the language model or vision transformer model. So this way, actually, we can maximally maintain the original information. There is no such kind of bottleneck, information bottleneck anymore. So we can feed the information to the upper layers of the transformer. So this way, we can still control the number of the context length, for example, 576, but still get a very good performance, right? And we can further enhance the vision transformer in a similar manner, the deep stack V. So we just put the visual tokens in the different layers of the vision transformer so that, okay, the final output is still 576, but it can significantly improve the performance for the multimodal tasks across the whole, across the board. So this is very kind of easy, but also very, very effective strategy. So we are just trying to advocating that, okay, putting the visual tokens into language model is not only just using, okay, the sequential way from left to right. We need to think about, okay, from bottom to the top, or even any other type of topologies, right? So like I just mentioned, so we can use the deep stack strategy for language model, the language model block or transformer layers. We can even, okay, use this exactly the same strategy for the vision transformer to enhance the vision transformer part. So both of them actually can significantly improve performance, especially for the high resolution tasks, and it can still maintain very good limited number of tokens and compute. And furthermore, we can further enhance the performance by even using a very high resolution, even we have a very long sequence, for example, like Lava 1.6. And we can use this same strategy to still have the 2K context length, but it can support up to 10K or 14K number of visual tokens. So this probably will tell you that, okay, so maybe you have a video, probably you can use this strategy, right? You can take much, much larger number of tokens if you have multiple layers in the transformer. And when your language model is becoming larger, you have more layers, and your each of layer is more capable, probably may even give you more kind of gain, right? This is very interesting finding from our work. Okay, so to summarize, how to cope with visual tokens for language model. So early strategies like Q-former or simple concatenation, then projection, they're pretty simple. But recently, actually, people really use Q-former. A lot of people, I discussed with a lot of people, we always think, okay, Q-former is great. But the problem is that, okay, we need to train it very maturely and fully. Otherwise, it can hardly revert, okay, the simple kind of simple kind of flattened visual token used in Lava or Mini-CV4X or many of the other works. So the second is that, okay, we are facing is a curse of the visual tokens. We want to propose some kind of visual token reduction or compression strategy. Some strategy like adaptive sampling, nested or elastic organization like Matryoshka way or some other way. And in the last, actually, we recently also introduced a stacking strategy. So we should jump out of the box. We should not only string the visual tokens into a sequence from left to right. We should jump out of the box and we should think differently to stack the visual tokens to different layers. So this is another strategy we want to mention and discuss. Yeah. Okay, so talking about the visual prompting. So basically, in the first two parts, we have already introduced how to leverage the different type of visual token adders, and how to cope with the large amount of visual tokens. And in the last part is visual prompting. The reason why, okay, we want to do visual prompting is that, okay, we have seen a lot of works in textual prompting, and we are seeing the magic power in language model by using different type of textual prompting. Here, the question is how to perform the visual prompting for large multimodal model, as many people just did for text. So in language model, actually, we have seen a lot of kind of prompting, like chain of sort is most of the famous one, and the chain of code and the problem of sort, etc. So this is pretty simple, right? So it's just simply, okay, put the sentence and ask the language model to, ask the language model to think step by step, to perform the reasoning step by step, then some magic happens. And this is a concrete sample from the chain of sort. Indeed, okay, given some kind of chain of sort and also in context few sort example, the whole kind of prompt can help the model to ignite more kind of capable reasoning capability compared with the baseline model on the left side. So the question is, given a large multimodal model, what kind of visual prompting we want to use? We want to use to empower the original multimodal language model or large multimodal models, right? And we want to draw inspiration from the visual community. Actually, we are in the visual community. So why visual prompting would benefit? So images are not only semantic, it's also visual and spatial. It's not like, okay, some some textual token in our brain, and we just spit it out. We just, okay, chat it out, right? The difference is that, okay, the visual signal is raw signal, the visual signal is spatial, and even 3D, etc. You can see here, so even in the 2D domain, actually, we have the bounding box, we have the different object in the image, even we have different type of mask or segmentations from the image. And based on this, actually, people in last year, I also introduced most of these works last year in the tutorial. So last year, actually, a lot of people trying to propose some kind of visual prompting for visual foundations. No one ever tried to apply this kind of visual prompting for large multimodal models. But the techniques are very kind of powerful. So they can significantly improve the flexibility and the interactive ability for the vision foundation, like SIM, like SAM, SIGGPT, and improve, etc. And this year, actually, we also have some new work called DynoV and T-Rex2. DynoV will be appear in CVPR as well. So we further enhance the visual prompting by unify different type of tasks, not about grounding, not only grounding, but also the example-based detection and grounding as well. So to summarize, actually, there are two types of visual prompting for large vision model. One is a visual feature prompting. The visual feature prompting means that, okay, people usually need to extract the visual feature from the vision encoder and use this feature as a prompt to feed into the decoder, for example, to generate some mask, generate some kind of fine-grained output, etc. And usually it's need additional module to encode this visual prompt. For example, like SAM, then use some kind of encoder, the special encoder to encode the bounding box, encode the point, etc. And SIM also use some kind of sample strategy to sample the feature and use another projection layer to project. And this strategy actually indeed requires some kind of additional annotations. Otherwise, actually, the model cannot understand, okay, how to how to extract the useful information from the regional feature from the vision encoder, right? And in comparison, there are some other type of visual prompting strategy, which is I call it visual pixel prompting, right? So the visual pixel prompting actually directly overlay the prompt on the images. It's organic to original large multimodal system. You don't need to retrain the model. You don't need to add additional model to the large multimodal, and suddenly it works. And it also of course, it relies on some kind of original imaging capability in large multimodal model, which I will talk about later. And first, I will talk about visual feature prompting for large multimodal model. So if we look at this figure, the only additional part is this part. So you need to have some kind of additional model to know and learn how to pull and how to sample the regional feature from the original image. And this region information is usually provided by user. And then, okay, use this visual token to replace the original textual token in the text prompt and feed this new organized textual prompt as input to the large language model. And finally, you will give the answer. And interesting, the answer, okay, will directly mention, okay, the region in the image is a space needle. It's not anymore the toy building, because in the text prompt, there's no toy building anymore. You are building an association between the toy building in the image and the textual token through the visual prompting strategy, right? So based on strategy, actually, we are seeing a lot of works. And some edit work, like I mentioned, for example, Sim or Sam, this type of work actually are trying to encode the visual prompt for vision foundation. And later on, we have seen, okay, GPT-4-ROI, Ferret, Pixel-M, etc., a lot of different works. And the overall pipeline or strategy is that, okay, the first need the fine-grained data set. So COCO, Ref COCO, Visual Genome, ACR, Object 365, etc. And second point is that, okay, they want to exhaustively support as many type of visual prompt as possible, like font, box, mask, stroke, because one of these type of prompt actually are very natural kind of HCI interaction kind of medium, right? So, and in terms of the feature sampler, people can use our LM, which has been already developed for a long time. And people can use even simpler one, the pooling, ROI pooling. And of course, there are some other works try to use this kind of special adaptive resampler, like the one used in Ferret or other type, several other works. So let's first look into the GPT for ROI. So for the GPT-4 ROI, so you can see here, given the image, and the user will draw some body box on top of the image. And based on this information, it will extract some kind of region feature from different layer of the vision token ladder, depending on the size of the bound box compared with the original image. And finally, okay, it will have one visual token for each of the region in the image and feed this different kind of visual feature into the token embedding sequence and feed this into the language model. And you will see here, compared with the original visual instruction tuning, like in Lava or many others, actually the difference is indeed, okay, already discussed and depicted in my last slides. Sorry, yeah. Yeah. So another work is called Ferret. So I'm sure Hawking this morning talked about a lot about Ferret. But here actually I'm mainly focused on the visual prompting part. So they propose a visual special adaptive visual sampler. So it's very similar to, for example, Sim or some other works. But the difference is that okay, they further enhance the kind of visual sampler through the spatial awareness. And they can, so that it can be adaptive to different type of shape, even though the shape is just is not a convex shape. It's like the cat tail, right, on the left side. So this way, actually, they can, okay, encode the region very well into a texture token and feed this text, the pseudo texture token into the language model. And in the meanwhile, they also associate the region with coordinate. I think this is another enhancement to the original visual sampler because the GPT-4 was only extracted the feature, but they did not, okay, further additionally provided the coordinate information in the text prompt. And this probably is also one of the reasons that for the good performance. And later on, actually, we also have the work called lava grounding. So in this lava grounding, actually, it's not only about the visual prompt encoder. We also introduced the visual grounding module, an additional module, which is much more capable compared to the original language decoder to decode the text, decode the coordinates. Here, actually, we additionally have the visual grounding module, which take the output from the language model as a prompt to further get a more fine-grained kind of segmentation mask or grounding result. On the right side, actually, Lava grounding can support as many as possible input prompt and also output modality output format. And you will see here, so given the task like describe the following image, and the whole kind of model can provide a very concrete kind of detailed description and also very concrete grounding on each of the regions, visual regions in the images. So compared with visual feature prompting, so the visual pixel prompting actually is even aggressive or even simpler. So the strategy is like we directly overlay the information on the image. For example, we directly draw a bound box in the pixel space on top of the image. And this way, we can directly build the association between the overlaid bound box or overlaid marks with the textual information or text description, like green box, like number 1, right? This strategy totally get rid of the vision prompt encoder. And based on this, actually, this strategy, the model can automatically, learn to or automatically generate some kind of very grounded description. Like the green box in the image is Space Needle. So because people know, where is the green box, right? And people can see where is the bounding box. That's why actually the grounding is building, is developed. Actually, in visual pixel prompting for large multimodal model, it's even grow faster than the visual feature prompting. The reason is very simple, right? People do not need to retrain the model. People only need to overlay some marks, overlay some bounding box in the pixel space, and then ask the model to ground it, ask the model to refer, ask the model to reason. So you will see a lot of work starting from maybe last year, October or something like that. But here I want to highly recommend you guys to read the red clip. So I would say, this kind of visual pixel prompting in large multimodal model, why, it works. One of the main reason is that, the clip model already learned some kind of good visual prompting understanding in the pixel level. And that's why actually later on, ourselves and many colleagues actually proposing different works. And we propose a set of mark, and it seems works very well and significantly unleash the power of the visual grounding even for GPT-4v. And if you look at different domains of the visual pixel prompting, so I cannot imagine that, this kind of simple visual pixel prompt strategy can already be used in so many domains, including the common computer vision domain, including the UI navigation domain, including the robotics or self-driving, etc. That's really, really kind of surprising. And in the middle, I want to mention the self-mark prompting, which we proposed last year, and it's very simple. And it was leveraged our previous works in our studies in the visual prompting for visual foundation. So the idea is pretty simple. So on the left side, we fed the image to the GPT-4v, and then, the GPT-4v fails very badly. So it cannot understand the spatial relationship between objects. It cannot reason about, the difference between two charts in the image to satisfy the user requirement. No, neither of them actually are correct. And once we overlay some kind of marks on top of the image, that's just it. That's only, what we additionally did. And suddenly, it ignites the grounding capability in the GPT-4v, significantly improve the performance, not only about the grounding, but also the visual reasoning. Look at the second sample. I want to find a seat close to windows. Where can I sit? You can see it on the chair number as 7 on the left side. It's close seat to the windows, represented by the arrow number as 1. So that's very interesting, right? So it even know, so because, it looks like, the region 1 actually have more light. And that's why you should sit in the chair 7 to get more natural light to work. So this is very surprising to me when I first prompt the model with CVPR. And the strategy behind this, actually, we got a lot of inspiration from our previous work and from other many works in the visual foundation model development, especially in the segmentation domain. So on the left side, we prompt the image with CVPR prompting and then feed them into the model. You will see, okay, it can significantly improve the performance for different type of tasks, cronting, even for counting, right? So how this kind of CVPR work? I think there are two essential kind of properties to make this CVPR work. The first is that we need to partition image into a set of semantically meaningful regions to align with the textual output. And this is also known as ability of grounding, right? So we need to make sure, okay, this mark or this any type of mark should be associated with some meaningful region. And this meaningful region should be semantically aware and should be semantic oriented. Otherwise, actually, it just have some kind of random pixel, right? And second is that the auxiliary information passed to the input image should be both interpretable and spokenable. Why is interpretable? Because it's required larger model to understand. Why is spokenable? Because you need to have a conversation with the language model. You need to, what the language model output should be understandable and conversationable, right, with user. So that's why actually we need to make sure these two essential property for the visual prompting, especially for the CVPR prompting. And behind this, based on this motivation, we leverage our previous work, like SIM, like semantic SAM, and also SAM. So we built a new CVPR prompting toolbox consist of different type of visual understanding or visual segmentation strategy to partition the image into different meaningful or different granularity, level of granularity of meaningful regions and overlay the marks on top of each of the regions. And it can support automatic way by using the SIM, semantic SAM, or interactive manner, right? And we further, propose different type of mark like mask plus number, mask plus alphabet, mask plus box plus number, etc. But we need to address some kind of practical problem. We do not want to make the marks too cloud, right? Otherwise, actually, there are some overlaps, and then it will have some kind of introduce some intervention between different regions or different meaningful regions for the language model. Then, we just develop a very simple strategy by sorting the region, all of the regions in the ascending order in terms of the error. And then we exclude the area regions when we overlay the new marks on the targeted region, on the current region. Yeah. So based on this, actually, we suddenly train the GPT-4V into some visual grounding model. And it can be off the shelf applied to the open vicarious segmentation, to the reference segmentation, to the video object segmentation, and to some other kind of grounded composition, etc. And on the right side, actually, we did some kind of proof of concept examination on top of different type of tasks. And then we found GPT plus some actually can even rival or outperform the well-trained vision model. So this is pretty surprising for us as well. And of course, we further leverage this technique to find some kind of error annotations in the Flickr 30K or in other type of data set. That's very interesting. And we can make it even wider. And you can see here, we can have some kind of interleaved conversation. By interleaving, which means that, we can interleave the mark and the text in the conversation between the GPT-4V, between the large multimodal model. This makes the conversation much more grounded and also flexible. And you can also find that, compared with the original GPT-4V, so this model actually can have more grounded information or guidance instructions to the user. This can significantly improve the usability of the original large multimodal model. I'm sure you guys probably saw some kind of social media posts like, how to determine which watermelon is the most sweetest, right? So that one actually is exactly using similar strategy, the sort of mark strategy. Put the mark on top of each of the watermelon, and GPT-4V will tell you which watermelon is the sweetest. And I think the success rate is very high according to different type of social media. Yeah. And of course, it can further help you to instruct you do this kind of tool usage and this kind of 2D game planning and also the simulated kind of navigation. So this capability originally was not observed in the GPT-4V, or even, okay, it's very weak in the original GPT-4V, but based on this, actually it suddenly emerges very well. And I will skip this. So there are some other works for the UI navigation as well, with using a similar strategy. And I will quickly go through the applications of visual pixel prompting for different type of tasks, even for the UI navigation. And this is one of the demo which come out just a few days, maybe 1 week or so after set mark prompting appears to the public. And they are building some kind of UI agent to help to navigate and navigate on the website. And this is another work our colleagues did. So for the smartphone UI navigation, they also overlay the marks on top of the image, and then, okay, ask GPT-4V which button or which region should be clicked. And this is another benchmark called Visual Web Arena. Actually, it's pretty difficult, I would say. So it's examining, okay, how to do the internet surfing on Reddit, how to read the Twitter, how to read different type of posts, right? So it's pretty hard, but they also found, okay, using this sort of mark prompting actually can significantly enhance the original GPT-4V, even though actually the final success rate is still very low, I would say. And also for the robotics. So people are trying to integrate these two type of strategy into the robotics domain as well. So for example, the first work is pivot. The pivot actually overlay different marks and also connect it with arrows. So this kind of strategy can help the robot to determine which direction to navigate. So this is pretty wide, right? So I never thought about this actually. So it can help you to guide the model, right? To find a direction and to further execute more actions step by step. So this is pretty interesting. Another work is called Mocha. So this work is for manipulation. The early work is for the navigation. This work is for the manipulation. And even for manipulation, actually, it needed to handle the object in a very fine-grained manner. And that's why I actually use different types of segmentation or some kind of localization techniques to localize the point or the affordance part, and finally tell the robot where to handle the object, which object to manipulate. And this is another related work, very similar. So to recap a little bit, so we earlier talked about the visual pixel prompting or visual feature prompting for visual foundation. Actually, this visual prompt strategy actually can be seamlessly integrated and introduced into the large multimodal as well. And the observation or the pros and cons actually are the same. So different type of visual prompt strategy actually have different type of pros and cons. So this will, especially for the visual pixel prompting, right? So as I mentioned here, it relies on the original imaging capability of large multimodal model. Actually, when we proposed the set mark, actually, I never found another large multimodal model can support this kind of capability. This is very interesting and very kind of miserable to me. So the question lead us to think about, can we build our own large multimodal support visual pixel prompting? And the answer is yes. So for example, one of the work is called VIP Lava. So they propose to train the Lava model to support different type of visual prompting on the bottom left corner. And there is no need for the complex region encoding, but achieve the state-of-the-art on region understanding in different tasks. And they also proposed the VIP bench to examine the visual pixel prompting capability for different type of model. And of course, in that way, actually, they can did a very good job on a subdomain images like Coco style image, because the model was trained on Coco style image. But in general, actually, it can still not fulfill different type of domains like robotics, like UI navigation, etc. So this still require more kind of effort. Another work is called SOM Lab. So SOM lava actually, as the name tells, right, it's combination of the SOM system mark pumping plus lava. So they also have developed some clean version of the instruction training data for the set mark pumping, overlay some marks on top of the image, and then train the model, instructively tune the model to learn or to associate the marks with the region in the image. And you can see here, if you fully train a model, it can even outperform the GPT-4v on this kind of in-domain tasks. For example, the top part you will see with the number of training data listing item one by one, then at some point actually the performance can even outperform I think most of the time actually outperform the GPT-4v. Yeah, that's very interesting. And also on the bottom part, actually, compared with the original Lava 1.5, you enforce the model to list the item one by one through the sub-mark pumping. Actually, it can also improve the performance, especially for some kind of spatial reasoning and grounding, like POPE or some kind of MME, etc. So this is what very interesting finding. Even though they only use maybe 100K or even less number of instruction training data. And in the last, actually, I think another problem arises. So rather than, specially tune your model to support this visual pixel prompting, what else? Whether we can have a new model which does not train on this kind of task specifically, but still emerge some capability. And the answer is yes. We recently actually developed the Phase3 vision, and it was developed on top of the Phase3. And Phase3 actually have a very good performance on large language model benchmarks, but we do not care about this here. But if we apply this kind of Phase3 to the vision modality, and we already achieve very, very good performance on the first column, you will see it only has roughly 4.2 billion parameters, but it can cover a lot of other stuff that are add open source, work closed source across the board. But of course, this is not the important part in this talk. So, and of course, this part actually also shows some kind of fine grained understanding ability of the OCR or document understanding or screenshot, and also it can produce very good kind of formatted text output. Again, this is not what we want to show. So we want to show here. So we apply the same image, the same prompt to Phase3 vision, and you will see that, the model, the Phase3 vision model actually also have such kind of emerging self-mark prompting capability. You ask, what should I sit if I want to have a laptop? And the answer is you should sit on step child 8 to have a lamp, as it is the only chair with a lamp on the desk. So it will already give a correct answer. On the right side, actually, if I directly ask what is 3, the number 3 is associated with a garnish on top of fish. So it can understand, there should be some association. They should have some kind of implicit association through the conversation. So basically, this means that, the GPT-4v visual pixel prompting actually is not a mystery anymore. So actually, we can even have some kind of pre-trained model, a small multimodal model actually can have such kind of capability emerged. This is very interesting. Actually, this also answers the question I proposed in the paper of the set mark in the end. So to summarize, so how to perform visual prompting for large multimodal model as for text. So usually, we have two types of visual prompting strategy, the feature-based and the pixel-based. And both have pros and cons, right? So the feature-based one actually require additional annotations. The pixel-based one actually is much easier to apply, but it's not guaranteed that your model have such kind of capability. So this is pretty kind of uncontrollable in terms of the trained one. And also, indeed, we found that, so the multimodal can be trained to obtain such kind of visual prompting strategy, especially for the visual pixel prompting strategy. And we have already seen in the Phase3 vision, even though it's pretty small. So in the interest of time, so I will skip this part, the challenge opportunities. I'm sure that you guys probably already think of different type of challenges and opportunities in your own work, but I will list a few of them. The current large multimodal model still falls short of easy tasks like like spatial reference and reasoning. And of course, counting, still bad. Even we coder actually introduced some way to improve, but it's still not that good. And also the planning is bad. It cannot play Go. And also understanding humor in the image is bad. It can only answer some kind of very high level, kind of give very high level answer. Causal effect reasoning, very bad. Of course, navigate as an agent is very bad. I just mentioned that, okay, there is a huge gap between the most capable model and the human performance in terms of their access rate of website navigation. It's still a very, very huge gap as indicated in this virtual agent arena. Of course, we have more type of benchmarks and more challenging tasks, and of course, more opportunities. For example, this one actually have a more kind of challenging task, and when it requires more capable vision model or multimodal model. And this is another one for multiple images. And this is another kind of advanced primary strategy, which include a set of mark as a subset or something like that. And more understanding of the videos. I'm sure okay, people in this morning actually talk about this much. And some other kind of benchmarks. We require more benchmarks to evaluate the visual reasoning. And finally, actually, how we can really, okay, train the large multimodal to be capable of reasoning and planning in the physical world, in the real world, like robotics, autonomous driving. This is definitely very exciting domain to explore. Okay, so thanks for your attention and enjoy your stay at Seattle.